formulas. Take a look at, now that we know how to solve equations with variables on both sides, we're going to look at putting a few extra variables in there and actually just solving for one of those variables, or maybe another one of those variables, and just move the variables around and see how they look in various different situations and how we can manipulate those formulas. So without further ado, let's take a look. Just a review here. Formulas, right? For those of you who don't know, we've worked with some formulas already. They're just equations that show up in a lot of the time in the sciences, but in other places as well. You've already seen them in math. One of the things that they do is they've already been calculated as ways for us to understand something particular very quickly. Oftentimes, especially in physics and chemistry, formulas contain more than one variable, and if you one of those common ones you might have seen in the first slide is like E equals mc squared. Energy equals mass times the speed of light squared. So just kind of throwing that together again, E equals mc squared is the formula that Einstein is famous for. E is energy, and that is equal to mass. So the mass, the size or the weight of the object, multiplied times c is the speed of light. And if you take the speed of light and you square it, I know, that's a massive number, right? Okay, and then you multiply times the mass. That gives you the energy of that particular object, depending on the size of the object, right? That's where the mass comes in. Okay, so the energy produced by an object is given by this formula, right? Which is kind of cool. But you can manipulate this formula in various different ways. We'll take a look at how to do that. So here is a physics example. D equals VT, right? D equals VT, the variables, they stand for distance, velocity, and time. This is something that if you go into any of the sciences, you will very likely use this formula, even in basic science. So distance, velocity, and time, you might not have all of those, right? So let's look at what that looks like. So if we've got D equals VT, how do we solve the equation for T, right? Okay, so this means that we want T to be equal to the rest of the equation, right? We want the equation to say T equals. So instead of saying D equals VT, we want to say T equals whatever. Okay, so what does it mean to do that? So we're going to use inverse operations to do that. So let's take a look at what that and how we're going to do that. So inverse operations, we've done it before. It's just about adding, subtracting, multiplying, and dividing the opposite of what you've got on both sides of the equation until we get what we're looking for. Okay, so we're going to solve it for T. D equals VT transferred to T equals something. Let's take a look. So we're going to say, here's T, right? It's being multiplied by V. How do we undo that multiplication? Well, we know that the inverse of multiplication is division, so we're going to divide both sides by V. Here we go, right? Here's T. It's being multiplied by V. We undo the multiplication by dividing both sides by V. We do that on both sides. We notice that what's going to happen now is that those V's are going to cancel out, right? Those V's are going to cancel out. And look at that. Now we have D over V equals T, so, or T equals D over V. So we went from D equals VT, right here, one way of representing it, to T equals D over V. We could have done the same with V, of course. We could have found that V is equal to D over T, right? So, just using inverse operations. All right. So there was a rogue slide in there. So another popular formula here, this is something that you're very familiar with from Algebra 1, or even from 8th grade math, y equals mx plus b. So the formula for linear equations, slope-intercept, the slope-intercept form of a line. Okay, so what if you want to find out what m is, the slope? You don't know what m is, and you want to find out what it is based on the rest of the information you have. How do you find out what m is? Well, we know that m is the change in y over the change in x, but in this context, when you just have y, x, and b, what does that mean? So, once again, we're just going to look at this as we look at numbers. M is stuck in there, right? We can't get to m without getting rid of b at x first. So we're going to start, right? We're going to start by subtracting that b from both sides. Okay? So when we subtract the b from both sides, now we have y minus b equals mx. Nice. That's the first step. Okay? So two-step equations. The next step is going to be to divide by the coefficient of m. In this case, the coefficient of m is x, right? We're just not, the point here is it's exactly the same as what we've done before, except we're just doing it with letters instead of numbers, right? And we divide by x on both sides, and that gives us y minus b over x equals m. Very nice, right? Okay. Or another way, of course, of writing that would be m equals y minus b over x. It's kind of, we like to see that on the variable we're looking for on the left side of the equation. So, even if your equation is all variables or a mix of variables, you can and numbers, you can still use simplifying and solving strategies to solve. So all of this, everything that we've learned, from the adding and subtracting on both sides to multiplying, dividing on both sides, the distribution, the combining like terms, all that stuff, right? Those inverse operations in particular, we can do that with any equation to solve for a part of that equation. It doesn't matter what we're solving for a number or solving for a letter. We can do whatever we want, right? Just as Raccoon here is saying, is nothing can stop you, right? Which is really nice. Okay. Here's a few examples right here, okay? And I'll run through these for you, okay? So a few examples real quick. If we want to solve for k, k is on the left-hand side here. We've got a 20 in the way, so we're going to subtract 20 from both sides. And that, of course, gives us k equals t minus 20. Not too bad, right? I mean, we're not looking for a perfect, the key thing here is we're not looking for a perfect, like, one number answer. We're just looking to find out, well, how do we represent this variable k in terms of everything else? Okay? Solving for v is divided by 5 over here. So, well, the inverse operation of division is multiplication, so we're going to multiply both sides by 5. And that gives us v equals 5w, or w times 5. 5w, w times 5, same thing. Okay? All right, solving for m here, we've got 3 variables here, doesn't matter, right? M is stuck in here with a coefficient, and there's a subtraction going on. We're going to add the p to both sides first, right? When we add the p to both sides, we get 2m equals 11f plus p. Now this is a super ugly solution. When we divide both sides by 2, we get this whole big nasty pile of garbage over here, right? But this is indeed our solution, right? That's your solution for m. So, because of course you're canceling out the 2's on both sides, right? So you've got, that's equal to m. Ugly, right? But still true, okay? Remember, we're not really looking for a perfect one number solution to anything. We're just looking for representing everything in terms of that one variable we're solving for. XYZ is similar, right? XYZ plus a, right? Subtract a from both sides. and we get x, y, z equals 10 minus a, and we're solving for y. Notice that y is multiplied by x and it's multiplied by z. We could do this all together, or we could do it all at one. What we're going to do is we're going to kind of look at that x, y, z. We're going to say, well, that's y times x, z. How about that? Put parentheses around the x, z, and that's going to work for us. So we're going to divide both sides by x, z, and boom, y equals this nonsense up here. Okay? And it's okay. Doesn't need to make perfect sense, right? Presumably you have numbers that you plug in then for x and z and a, and you'll be able to solve out what y is. You just don't have a number for y yet, you know? So that's why you need to rewrite the formula, okay? A few other examples. Let's take a look at a few other examples real quick. I won't go through the whole worksheet because it's very monotonous. It's the same kind of thing over and over and over again. Okay. There's our. I showed you the worksheet. The slideshow is also showing you. Okay. Same idea, right? Multiplying the inverse operation, right? 6 and 7. There's your xz going on right there. Okay. So, in a nutshell, this is no different from what we've worked with already in our inverse operations for solving for one variable and actually getting a nice fancy number out of it. In this case, we're just getting an expression, or we're getting an expression out of solving for one term. So, if you have any questions, please feel free to ask.